Thank you. Thank you, Mohammed, and thanks to the organizers for inviting me. So today I want to talk about four manifolds and exotic two-spheres. So about four-dimensional manifolds, and by two-sphere it's an S2, so a two-dimensional sphere, but not the sphere in itself. Usually it will be embedded in another four manifold. Okay, so the first part is gonna be an introduction. We're gonna talk about four manifolds in general. We will give examples. We will talk about the connected sum and how is dimension 4 special. We will talk about the intersection form, and then about the topological classification of four manifolds, which is the classification that we know now. Okay. So in this talk, we will be interested in the closed connected oriented case. By closed, I mean compact without boundary. And here are some examples. So first of all, the four sphere, which are the unit elements in R5, for example, and the complex projective space, or the second complex projective space, CP2, which is a space of lines, and it can be defined as C3 star over this relation, which gives a line. So CP2 is the space of all lines in C3. And we can also have some product manifolds, like S1 times S3, S2 times S2, T4, or sigma G1 in genus G1 surface times genus G2 surface. Pretty much any surface times another is the four manifold. You can have Fermat surfaces. These are complex surfaces, so they are four-dimensional, and they are defined as the zero sets of these polynomials. And you can have also another example is the K3 surfaces, which are an important class of complex surfaces. So they're four-dimensional. But when seen up to diffeomorphisms, they all become only one four manifold. And that's why topologists call it the K3 surface instead of K3 surfaces for complex geometers. So this K3 surface is actually also diffeomorphic to gamma for the Fermat surface. So just a second. Okay, so we have also the connected sum, which is a useful procedure to construct new manifolds. So what you do is you take two disks. If you have two manifolds, M1 and M2, smooth manifolds, you take two disks embedded in these manifolds, and you take phi and map orientation reversing diffeomorphism between these two disks, and you define the connected sum to be of M1 and M2. We have this ds sign to denote it, and it's M1 minus D1 glued to M2 minus D2 along the boundary by the map phi. So this is the picture pretty much. For example, if you have two tori's and you want to connect some, you need two disks inside them, and you remove the disks and you identify the boundaries. You glue them so you get a genus 2 surface in this case. So this is what the connected sum is, and it actually doesn't depend on the disk nor on the glue-in map. And we can also define NM to be like the connected sum of M n times. So now why is the dimension, not why probably, but how is it special? In what sense is dimension 4 special? So dimension 4 has a lot of exotic phenomena. By we mean the following, for example. So for n, a positive integer different from 4, for all dimensions different from 4, we have that in the open realm, we have if an n-dimensional manifold is homeomorphic to Rn, then it is also diffeomorphic to Rn. So by this, we mean Rn has a unique smooth structure. So if you take a topological Rn, it's also a smooth Rn. And for the closed manifolds, we have that for any dimension different from 4, there are only finitely many manifolds that are homeomorphic, but not diffeomorphic to Mn. So there are finitely many smooth structures. And these two theorems were by Moyes and Stallings, and the second one was by Stallings. Right? And in contrast, we have in dimension 4 that there is an uncountable family of 4 manifolds, homeomorphic but not diffeomorphic to R4, as opposed to like in all other dimensions, there's a unique one, which was theorem by Gomp and Taubes. And in the closed manifold, we have many manifolds that each have a countable infinity of other manifolds, homeomorphic but not diffeomorphic. So you have closed manifold that have infinitely many smooth structures, and these manifolds are not super crazy or something. For example, the K3 surface, which is very common in complex geometry or something. This has this property, exotic property. So now we talk about classification of 4 manifolds. So if we want to classify all 4 manifolds, there are theorems of Dan and Markov, which tell us that it's impossible. This is mainly due to the fact that all groups appear as fundamental groups of a 4 manifold. So this was a theorem of Dan, and then a theorem of Markov says that this using theorem of Dan says if you classify all 4 manifolds, then this will give you a classification or an algorithm to classify all groups or solve the word problem, so that's why it's impossible to classify all 4 manifolds. And then like the most natural or easiest thing to start with is the simply connected ones. So we restrict the fundamental group to avoid these complications. So if you take M closed oriented connected, simply connected 4 manifold, we have that the 0th homology and the 4th homology are going to be Z, and the 1st homology and 3rd homology are going to be 0. This is because it's simply connected. And okay, so we know these 4 homology groups, but do we know what the second one is? The second one, we don't know it, so it depends on the manifolds. A natural question would be that, is H2 enough to determine M? And the answer is no. That would be too nice to have. But no, for example, CP2 and CP2 bar. What is CP2 bar? CP2 bar is just CP2 equipped with the opposite orientation, and these two have the same second homology, but they are at different 4 manifolds. You can tell them apart by their cohomology ring, which we will discuss later how you can tell them apart. But for example, these are the simplest examples, which H2 doesn't determine the manifold. So to see what structure coming from the cohomology ring is responsible for this distinction, we can pin it down as the intersection form, and we will start to define it. So first, define the algebraic intersection number of 2 transversal oriented surfaces, S1 and S2, in an oriented 4 manifold M to be. So you take each point of intersection, you take it to be either 1, +1, or -1, depending if TPS1, the orientation of TPS1 followed by the orientation of TPS2 agrees with TPM. So for example, if you take these 2 curves in R2, you can see that the first point has the opposite orientation of the standard R2, and the second one has the correct one, so +1. Third one has, again, the opposite. So in total, it's -1 + 1 -1, it's -1. So in this case, the algebraic intersection number is -1. So we can start now to find what an intersection form is. If you take M to be closed oriented 4 manifolds, and alpha and beta two homology classes represented by smoothly embedded surfaces S alpha and S beta. So you can define the intersection form of M to be a map from H2 of M times H2 of M to the integers, such that you send the pair alpha beta to the algebraic intersection number of S alpha and S beta. Now this, at first sight, this needn't be well defined. Like if you change the representatives, first of all, why do representatives exist in the first place? That's not trivial, but they do exist. But then if you change them, do you get the same? The answer is yes, even if it is a well-defined map, because you can see it as the usual. There's the usual operation on the second homology, which is the cup product, and this cup product is defined, is well defined. So it will be this QM actually, if you up to a Poincare duality. So, but anyways, so this depends on the second homology and on the cohomology ring, and the cohomology ring is a homotopy invariant. So this intersection form is itself a homotopy invariant, and a homotopy invariant is slightly weaker than a homeomorphism, much weaker. But so this means if four manifolds are homeomorphic, they will also have the same intersection form. So, but if we wanna try to understand this intersection form more, so if M is simply connected, we will get that H2M is a free abelian group, Zn for some non-negative integer n, okay. And if you specify a basis for H2M, or you specify the diffeomorphism to Zn, the intersection form, you can see it as a bilinear form on Zn. In fact, it will be a symmetric unimodular form. So it can be represented actually by a symmetric matrix in GLN of Z. Okay, so we will often confuse the intersection form and the matrix representing it, as long as this doesn't affect anything. We will call them both QM. As long as the basis is well pinned down. So this is pretty much saying that the intersection form is actually a matrix, a unimodular one. So examples, what is Q of CP2? Q of CP2 is gonna be the 1-by-1 matrix, which has one, the identities. And Q of CP2 bar is gonna be -1. And this is how we differentiate the two manifolds. I mean, we know they are not the same, even though they have the same second homology. And Q of S2 times S2 is going to be this 0, 1, 1, 0, sometimes called the hyperbolic matrix, I think. Because the basis you can take here to see it is that, so you have S2 times S2 has second homology Z2, and you can write, okay. So S2 times S2 has second homology Z2 generated by the class of the first S2 times a point and by a point times S2, so the second S2. And we can see that the first one doesn't intersect itself. If you perturb it a bit, you can perturb the point in the other side. But each one will intersect the other in exactly one point positively. So this will be 0, 0, 1, 1, or 0, 1, 1, 0. On the other hand, QCP2 connected sum CP2 bar is gonna be 1, 0, 0, -1. So these are other manifolds that both have the same second homology, but their intersection forms are different, so they are different manifolds. how do we know? Actually, CP2 connected sum CP2 bar is a bundle, an S2 bundle over S2. So this also gives us a differentiation between the two S2 bundles over S2. And we have that. Yeah, we know the one before this by the general rule that Q of M1 connected sum M2 is gonna be just the direct sum of the intersections, because all surfaces in this one and this side in one side and on the other side are gonna be the same. You can show this. Is there any questions up to now? Okay, we can. Okay, we have the last example is that Q of M is always the minus QM bar. So the intersection form, if you switch the orientation of on M, you get M bar. This by definition, M bar is the M with the opposite orientation. And so if you remember this image, if you switch the orientation of R2, you are switching all the plus and minus signs. So what you get is minus the intersection form. QM is minus QM bar. So how does this intersection form help? So the first theorem is by Whitehead. I don't really know one, but like quite old one. So two smooth closed simply connected four manifolds M1, M2 are homotopy equivalent if and only if Q M1 they have the same intersection form or is congruent, similar intersection form. So the conclusion, if they have the same intersection form, the conclusion is that they are homotopy equivalent. Then there's the theorem of Friedman in 1982, which he got the Fields medal, that two smooth closed simply connected four manifolds, M1 and M2, are homeomorphic if and only if they have the same intersection form. So it's the same of Whitehead, but with a large jump from homotopy equivalence to homeomorphisms in the conclusion. And this pretty much gives us a topological classification of four manifolds by their intersection form. So the intersection form is the invariant you want to look at if you want to know what manifold do you have topologically up to homeomorphism. So one of the corollaries, the direct corollaries of this theorem is that if a four manifold X is homotopy equivalent to S4, it is homeomorphic to S4. This is also known as the four-dimensional Poincaré conjecture, which is also proven by Friedman as a corollary of his other theorem. So notice that in here, it is a homeomorphism. X is going to be homeomorphic to S4. It doesn't say whether it's going to be diffeomorphic or not. So this, whether it is or not, is one of the biggest open problem in four manifold theory and known as the smooth four-dimensional Poincaré conjecture. But one of the stuff that we know in the smooth direction in general about the classification is that if you use Friedman and you get a homeomorphism between M1 and M2, then the theorem of Wall from 1964 says that there exists a non-negative integer R such that M1 connected sum with R copies of S2 times S2 and M2 connected sum with R copies of S2 times S2 are diffeomorphic. So the theorem is pretty much saying that you can stabilize the manifolds if they were homeomorphic but not diffeomorphic. Then you add enough S2 times S2 to both sides, they will become the same. You will stabilize the smooth structure. It's called Wall stabilization theorem. So in general, in the conclusion of the theorem is that there exists a non-negative integer R. But then one can ask the question, is R bounded? Like how big can R be? And what we know This is also an open question, but what we know in all the examples we know, R is always 1. Like we do not know examples where it's bigger than that. So we can also ask the inverse question, which is that if you have a unimodular symmetric intersection form Q, is that a closed form manifold M with Qm isomorphic to Q? So the answer is also by Friedman in the same theorem as before, in the same result. Given so any unimodular symmetric in matrix Q, there exists topological form manifold M with Un isomorphic to Q. So he answers it in the topological category. Now, whether or not there is a smooth one, that is actually false, and there are many results. For example, Roslin's theorem, Donaldson's theorem, or Furuta's. They show that there are extra restrictions on the bilinear form to be an intersection form for manifold. So in general, finding which unimodular forms are intersection forms of smooth form manifolds, this is known as the geography problem. And one can ask it also for different fundamental groups or for specific properties of the manifold, like you can ask it for symplectic manifolds or for complex ones, and so on. So this concludes our first part. So do you have any questions?